close your eyes for a moment and imagine nothing. Not darkness, not emptiness, not even space itself. Just nothing. No past, no future, no present moment to speak of. This is what existed before time began. Or rather, this is what didn't exist at all. Welcome to a journey through the strange science behind time. Over the next 2 hours, we'll explore one of the universe's most mysterious dimensions. We'll travel from the very first moment time sparked into existence, through the peculiar ways it bends and stretches across the cosmos, to the question of whether time might one day come to an end. But let's begin at the beginning, or rather, at the moment there was no beginning at all. 13.8 billion years ago, something extraordinary happened. In an event we call the Big Bang, the universe burst into existence. But here's what's truly mind-bending. Time itself was born in that same instant. Before the Big Bang, there was no before. The very concept of before and after didn't exist. Time is not some invisible river that was always flowing, waiting for the universe to jump in. Instead, time and space came into being together, woven into the same fabric we now call space-time. Think about that for a moment. Time had a beginning. There was a first moment, a moment zero. Before that moment, the word before loses all meaning. It's like asking what's north of the North Pole. The question itself dissolves into impossibility. This is our first strange fact about time. Time itself has a birthday. It was born alongside space and matter and energy, all compressed into a point smaller than an atom, and then suddenly, explosively becoming. From that first moment onward, time began to flow. But here's something curious you've probably noticed. Time only flows in one direction. You can walk forward, then walk backward. You can drive north, then drive south. But you cannot move backward through time. You cannot unbreak a glass. You cannot unburn a log. You cannot grow younger. Scientists call this the arrow of time, and it points stubbornly toward the future, never the past. But why? What makes time so different from the other dimensions? The answer lies in something called entropy, which is a measure of disorder in the universe. Imagine a drop of ink falling into a glass of water. The ink spreads, diffuses, mixes until the water is uniformly light blue. You'll never see that ink spontaneously gather itself back into a drop. Things naturally move from order to disorder, from organized to chaotic. This is the second law of thermodynamics, one of the most fundamental laws in all of physics. And it's what gives time its direction. The arrow of time points in the direction of increasing entropy. The universe is constantly moving from a state of lower entropy to higher entropy, from more organized to less organized. That's why scrambled eggs never unscramble themselves. That's why we remember the past, but not the future. Memory itself is a product of entropy, of information being recorded in a directional way. Now, let me tell you something that might surprise you. Time doesn't exist separately from space. In our everyday experience, they seem completely different. Space is where things are. Time is when things happen. You can move through space, but you're dragged helplessly through time. But Albert Einstein, In perhaps his most profound insight, realized that space and time are not separate at all. They are two aspects of the same thing. Space-time, a unified, four-dimensional fabric that makes up the structure of our universe. Imagine you're meeting a friend. You don't just tell them where to meet you. You also tell them when. Let's meet at the coffee shop on Main Street at 3 o'clock. You need 4 coordinates, 3 for space and 1 for time. In a very real sense, time is just another dimension, similar to length, width, and height. This was Einstein's special theory of relativity, published in 1905. Space and time are woven together into a single fabric called space-time. Events don't happen in space at a certain time. They happen at specific points in space-time. You're not just moving through space as time passes. You're traveling through space-time itself. This might seem like a mathematical trick, a clever way of thinking about things, but not really true. But the universe doesn't care what seems obvious to us. And the evidence that space-time is real is overwhelming. Because once you realize space and time are connected, something remarkable follows. If you can bend space, you must also be able to bend time. Let's take a journey in a very fast spaceship. Not just airplane fast. Not even rocket fast. I mean truly, incredibly fast. Close to the speed of light, which is about 186,000 miles per second. As you accelerate to these incredible speeds, something strange begins to happen. Time itself starts to slow down for you. Not in some metaphorical sense. Not just feeling like time is slow. Time actually passes more slowly for you than it does for people back on Earth. If you traveled at 99.9% the speed of light for what felt like 1 year to you when you returned to Earth, you'd find that about 22 years had passed for everyone else. Your friends would be older. The world would have changed. But you would have aged only 1 year. This is called time dilation, and it's not science fiction. It's science fact. The faster you move through space, the slower you move through time. It's been measured, verified, tested in countless experiments. Atomic clocks flown on airplanes run slightly slower than atomic clocks on the ground. Particles accelerated to near light speed live longer than they should because time slows down for them. Why does this happen? Because the speed of light is the same for everyone, no matter how fast they're moving. That sounds simple, but it has profound consequences. If light always travels at the same speed, then time and space themselves must be flexible to make that work. As you move faster through space, you must move slower through time so that light's speed remains constant from your perspective. You're always moving through space-time at the same total speed. When you sit still, all your motion is through time. When you move through space, some of that motion through time converts into motion through space. Move fast enough through space, and your movement through time slows to a crawl. But speed isn't the only thing that affects time. Gravity does too. And this is where Einstein's theory becomes even more beautiful and strange. In 1915, Einstein published his general theory of relativity. He realized that gravity isn't really a force in the traditional sense. It's a curvature of space-time itself. Massive objects like planets and stars bend the fabric of space-time around them, the way a bowling ball creates a depression in a stretched rubber sheet. And if gravity bends space-time, then gravity must bend time. The stronger the gravity, the slower time passes. Time moves slower in stronger gravitational fields. If you stood on the surface of a massive planet with intense gravity, time would pass more slowly for you than for someone floating far away in space. This has been measured too. Atomic clocks on the ground run slightly slower than atomic clocks on mountaintops because they're deeper in Earth's gravitational field. GPS satellites orbiting high above Earth have to account for both the gravitational time dilation from being farther from Earth's mass and the speed-based time dilation from their orbital velocity. If they didn't correct for these effects, GPS navigation would be off by miles within hours. On the surface of a neutron star, where gravity is incredibly intense, time would pass about 30% slower than it does on Earth. And at the edge of a black hole, at the point called the event horizon, time dilation becomes infinite. Time essentially stops from the perspective of someone watching from far away. This is why, if you watch someone fall into a black hole, you would never quite see them cross that boundary. They would appear to slow down, freeze, fade, but never quite disappear because from your perspective, they're experiencing time infinitely slowly. We've talked about moving fast and how it affects time. But how fast can something go? Is there a limit? Yes. There's an absolute speed limit built into the structure of the universe. The speed of light. Nothing with mass can reach it. Nothing with mass can exceed it. No matter how much energy you pour into accelerating something, it will never quite reach 186,282 miles per second. Why not? What makes light speed so special? The answer comes back to space-time. As you accelerate closer and closer to light speed, something strange happens. Time slows down more and more. Distances contract in the direction you're traveling. And your mass, from the perspective of a stationary observer, increases. The closer you get to light speed, the more energy it takes to accelerate even a tiny bit faster. To actually reach the speed of light, you would need infinite energy. Your mass would become infinite. Time for you would stop completely. These aren't just practical difficulties. They're fundamental impossibilities built into the fabric of reality. The speed of light is the universe's ultimate speed limit, and nothing with mass can reach it. Light itself travels at this speed precisely because photons, the particles of light, have no mass. They're born moving at light speed and can never do otherwise. But here's something to ponder. Why does this speed limit exist at all? Why is the universe structured this way? Scientists believe it has to do with causality, with cause and effect. If you could travel faster than light, you could, in principle, travel backward in time. You could arrive at a destination before you left. You could receive a message before it was sent. The universe would stop making sense. Causes wouldn't precede effects. The fundamental logic of reality would break down. The speed of light isn't just about light. It's the speed of causality itself. It's the speed at which cause propagates to effect, at which information can travel, at which any influence can move from one place to another. It's woven into the deepest structure of how things can possibly work. Let me ask you a question. What time is it right now? You might look at a clock and give me an answer. But here's the strange truth. The concept of right now is more complicated than it seems. Einstein's relativity tells us something shocking. There is no universal present moment. There is no cosmic now that encompasses the entire universe simultaneously. If you're sitting still and I'm moving fast relative to you, we will disagree about what events are happening now at a distant location. Events that I consider to be happening right now, you might consider to be in the past or future. We would both be correct. There's no objective answer to which of us is right about what's happening now on a planet in another galaxy. This is called the relativity of simultaneity. Two events that are simultaneous for one observer may not be simultaneous for another observer moving at a different speed. The present moment is not a universal slice through time that everyone experiences together. It's different for different observers, depending on their motion and position in space-time. Think about what this means for your experience right now. The now you're experiencing includes things happening around you. But for someone on the other side of the galaxy, because of the vast distance and the limitations of light speed, your now and their now don't line up in any meaningful way. In fact, because of relativity, there's ambiguity about whether what you're doing now is in their past, their present, or even their future. Time, it turns out, is not the universal, absolute thing we thought it was. It's personal, local, dependent on your motion and your position in a gravitational field. The universe doesn't have a master clock ticking away the moments for everyone simultaneously. Instead, each of us carries our own time with us, experiencing our own personal flow through the moments. We've covered a lot of strange territory in these first 20 minutes. We've learned that time had a beginning, that it flows in only one direction because of entropy, that it's woven together with space into space-time, that moving fast or experiencing strong gravity makes it slow down, that nothing can exceed light speed, and that there's no universal, now shared across the cosmos. These aren't just abstract ideas. They're the reality of the universe you live in. Every moment you experience, every second that ticks by, is part of this grand, strange, beautiful structure called space-time. In our next segment, we'll explore even stranger territory. We'll talk about what time means at the quantum level, where particles can seem to influence each other instantaneously across vast distances. We'll discuss time crystals, structures that repeat in time the way ordinary crystals repeat in space. And we'll ponder the ultimate question: could time itself come to an end? But for now, take a moment to simply exist in your own personal flow of time. Feel it moving forward, carrying you from past to future, moment by moment. You're traveling through space-time right now, at exactly 1 second per second, on a remarkable journey through the cosmos. Rest in that thought. Breathe. And when you're ready, we'll continue our exploration together. Part 2, Time in the Quantum Realm. Welcome back to our journey through time. In the first part of our exploration, we traveled from the birth of time itself through Einstein's revelations about how time bends and stretches with motion and gravity. We discovered that time is not the fixed, absolute thing we experience it to be, but something far stranger and more fluid. Now, we're going to venture into even more mysterious territory. We're going to shrink down to the quantum realm, where the rules that govern everyday life begin to break down, where particles behave in ways that seem to defy common sense, and where time itself becomes something altogether different. So take a deep breath, settle in, and prepare to explore the smallest scales of reality, where time plays tricks that would seem impossible in our everyday world. Imagine you could shrink yourself down to the size of an atom. You would enter a realm that operates by completely different rules than the world you're used to. This is the quantum realm, where particles can exist in multiple states at once, where the act of observation changes reality, and where the very fabric of space and time becomes grainy and uncertain. At these incredibly tiny scales, something remarkable happens to time. It becomes uncertain, fuzzy, subject to quantum fluctuations. Just as there's a fundamental limit to how precisely you can know both a particle's position and momentum at the same time, Heisenberg's uncertainty principle, there's also a limit to how precisely you can know energy and time together. In the quantum realm, time becomes uncertain and probabilistic. Over extremely short intervals, what we call quantum timescales, energy can fluctuate wildly. Pairs of particles can pop into existence out of nothing, live for the briefest instant, and then annihilate back into the vacuum. These are called virtual particles, and they exist because of the uncertainty in time and energy. The vacuum of space isn't truly empty. It's seething with these quantum fluctuations, particles borrowing energy from the universe for infinitesimally short periods, then paying it back before anyone notices. The shorter the time interval, the larger the energy fluctuation can be. Time, at the quantum level, is not smooth and continuous but choppy, granular, filled with uncertainty. This has real consequences. These virtual particles affect the behavior of real particles. They're responsible for forces like electromagnetism. They contribute to the energy of empty space itself. The quantum uncertainty of time is not just a mathematical curiosity. It's written into the fundamental nature of reality. Now let me tell you about one of the strangest phenomena in all of quantum physics: entanglement. When two particles become entangled, they form a connection that transcends ordinary space and time. Measure a property of one particle, and you instantly know the corresponding property of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he didn't like it one bit. It seemed to suggest that information could travel faster than light, that cause and effect could happen simultaneously across vast distances, that the universe was fundamentally non-local in a way that violated relativity. But experiments have proven again and again that entanglement is real. Entangled particles share a connection that appears instantaneous across any distance. Change the state of one, and the other changes immediately, whether they're separated by inches or by light years. Here's the crucial detail that Einstein missed. While the correlation is instantaneous, no usable information actually travels between the particles. You can't use entanglement to send a message faster than light. You can't use it to communicate. The correlation exists, but it can't be exploited to violate causality. Think of it this way. Imagine you have a pair of magic coins. You take one and give the other to a friend who travels to another galaxy. When you flip your coin and it lands on heads, your friend's coin will land on tails instantly. But you can't control whether your coin lands on heads or tails. It's random. So while there's a correlation, there's no way to encode a message. What entanglement really tells us is something profound about the nature of reality. The universe is not made of separate, independent objects that only interact through local contacts. At the quantum level, things that have interacted in the past remain connected in a deep, fundamental way. Space doesn't separate them as completely as we think. The quantum realm respects different rules about what it means for things to be separate or connected. And time? In the mathematics of quantum mechanics, time appears differently than space. Space is quantized, made of discrete chunks at the smallest scales. But time, in standard quantum theory, is still treated as smooth and continuous, flowing in the background while quantum events unfold. This asymmetry between space and time in quantum mechanics is one of the great unsolved puzzles of modern physics. In 2012, Nobel Prize-winning physicist Frank Wilczek proposed something that sounded like pure science fiction: time crystals. To understand what these are, let's first think about ordinary crystals. A crystal is a structure that repeats in space. Table salt, diamonds, snowflakes, these are all crystals. Their atoms are arranged in patterns that repeat over and over again in 3 dimensions. They break the symmetry of space, meaning they look different depending on where you look at them. Wilczek asked, could there be structures that repeat in time the same way crystals repeat in space? Could there be a system that returns to the same state periodically, oscillating forever, without using any energy? According to the laws of thermodynamics, this should be impossible. Things should always be moving toward equilibrium, toward disorder, toward stillness. A perpetual motion machine violates the fundamental rules of physics. And yet, in 2016, physicists created the first time crystal in a laboratory. Time crystals are quantum systems that oscillate periodically in their ground state, creating a pattern that repeats in time. They're not perpetual motion machines in the classical sense because they exist in their lowest energy state. They're not doing work or producing energy, but they're oscillating, changing, moving through a cycle, all while staying in equilibrium. How is this possible? The answer lies in quantum mechanics. In quantum systems, the ground state, the lowest energy configuration, doesn't have to be static. It can have structure, including temporal structure. Time crystals exploit this quantum loophole. They're systems where the lowest energy state involves periodic motion through time. Think about it. Just as regular crystals break the symmetry of space, they have special directions, special positions. Time crystals break the symmetry of time. Most laws of physics don't care what time it is. They work the same whether it's Tuesday or Thursday, morning or night. But in a time crystal, there is a preferred phase, a special moment in the cycle. Time itself becomes structured, patterned, crystallized. Time crystals exist at the boundary between classical and quantum physics, between the world we see and the hidden realm beneath. They remind us that time is not just an empty stage on which events unfold. Time can have structure. Time can have texture. Time can crystallize. How short can a moment be? Can you divide time into infinitely smaller and smaller intervals? Can you have half of a second, then half of that, then half of that, continuing forever? According to our best theories, the answer is no. There appears to be a fundamental limit to how finely time can be divided, the Planck time. The Planck time is approximately 0.000000000000000001 seconds. That's a decimal point followed by 43 zeros and then a 1. It's so short that more Planck time units occur in 1 second than seconds have occurred since the Big Bang. The Planck time is thought to be the shortest interval of time that has physical meaning. Below this scale, our current theories of physics break down. Space and time themselves may become so warped by quantum fluctuations that the very concepts of space and time cease to have meaning. At the Planck scale, quantum mechanics and general relativity collide. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles and fields at the smallest scales. These two theories are incompatible. They give different answers when you try to apply both at once. We need a theory of quantum gravity, a way of understanding how space-time behaves when both quantum effects and gravitational effects are strong. String theory, loop quantum gravity, and other approaches all try to solve this problem. And most of them suggest that space-time itself is not infinitely divisible. At the Planck scale, space might be made of discrete, indivisible units, like pixels on a screen. Time might tick forward in discrete Planck time steps, like frames in a movie. If this is true, then time is not fundamentally continuous. It's quantized. Reality doesn't flow smoothly from moment to moment, but jumps in the tiniest of hops, billions upon billions of times per second, far too quickly for us to ever notice directly. This is one of the deepest questions in physics. Is time continuous or discrete? Is it infinitely divisible? Or does it come in minimum units? The Planck time suggests an answer, but we don't yet have the complete theory to know for sure. In 1949, physicist Richard Feynman had a peculiar idea while thinking about antimatter. Antimatter particles are the opposites of ordinary matter particles. An electron has a negative charge. Its antimatter counterpart, the positron, has a positive charge. When matter and antimatter meet, they annihilate in a burst of energy. Feynman wondered, what if an antiparticle is just a regular particle traveling backward in time? It sounds absurd, but the mathematics works beautifully. In quantum field theory, the equations that describe particles moving forward in time are identical to the equations describing antiparticles moving backward in time. Antiparticles can be understood as ordinary particles moving backward through time. Imagine an electron moving through space-time. It follows a path, a world line, tracing its journey from past to future. Now imagine that world line suddenly reverses direction in time, heading backward. From our perspective, watching from the forward-moving time direction, This backward-moving electron would look exactly like a positron moving forward. This isn't just a mathematical trick. It has real consequences. When an electron and positron annihilate, you can think of it as a single electron encountering a moment in space-time where it reverses direction, turning from an electron moving forward in time into an electron moving backward in time, which we see as a positron. The world line bounces, creating the illusion of two particles meeting and destroying each other. Feynman even speculated, half seriously, that perhaps there's only one electron in the entire universe, bouncing backward and forward through time, weaving a vast tapestry through space-time, appearing to us as all the electrons and positrons that exist. This probably isn't true. There are far more electrons than positrons in the universe, which would be hard to explain with a single bouncing particle. But the idea captures something profound about the symmetry between matter and antimatter, and about the strange relationship between particles and time at the quantum level. Time in the quantum world is not the rigid one-way street we experience. In the mathematics and deep structure of reality, time has a flexibility, a reversibility, that doesn't appear in our everyday world. Particles can, in a certain sense, influence their own past. Effects can, in the quantum realm, precede their causes. Here's another mind-bending idea about time from the quantum world, this time from John Wheeler and Richard Feynman working together. They asked, what if cause and effect work differently than we think? What if the future can influence the past? In standard physics, causes precede effects. You flip a light switch, cause, and the light turns on, effect. The arrow of causality points the same direction as the arrow of time. But Wheeler and Feynman proposed a radical idea. Waves can travel both forward and backward in time, creating a symmetry between past and future. When you flip a light switch, it sends an electromagnetic wave forward in time that hits the bulb and causes it to glow. But according to Wheeler and Feynman, that bulb also sends a wave backward in time. This backward traveling wave goes back to the moment the switch was flipped. The two waves, one from the past, one from the future, meet in a handshake that creates the present moment. This isn't science fiction. The Wheeler-Feynman absorber theory is a legitimate interpretation of electromagnetism. It produces the same predictions as standard electromagnetic theory, but with a completely different philosophical understanding of how cause and effect work. In their interpretation, every event involves both forward and backward waves in time. The past influences the future, and the future influences the past. There's a symmetry, a give and take across time that we normally don't think about because we only perceive one direction. Why don't we notice these backward traveling waves? Because they require perfect absorption in the future. Every outgoing wave from the past must be completely absorbed by matter in the future, which then sends the backward wave. In our expanding universe, with its particular arrangement of matter, this creates a net forward flow of causality. But the underlying structure includes both directions. Experiments in quantum mechanics have actually observed similar phenomena. Quantum particles can be affected by measurements that are made in their future. The results of a detector setup tomorrow can influence the behavior of a particle today. The future, in quantum mechanics, is not completely independent of the past. They're entangled across time in ways we're only beginning to understand. Let's talk about one of the deepest mysteries in quantum mechanics, the measurement problem. In the quantum world, particles don't have definite properties until you measure them. Before measurement, an electron doesn't have a specific location. It exists in a superposition, a combination of many possible locations at once. Only when you observe it, when you measure where it is, does it collapse into a single, definite location. This is strange enough, but it becomes even stranger when you think about time. The measurement problem is fundamentally about the flow of time and the unfolding of events. Before measurement, the quantum state evolves smoothly and predictably according to the Schrödinger equation. It's deterministic, reversible. You can run the equations backward and forward in time. But when measurement happens, something different occurs. The wave function collapses. Superposition becomes actuality. Many possibilities become one reality. This collapse is not reversible. You can't uncollapse a wave function. Once the measurement has happened, the past is fixed, and the particle has a definite history. The act of quantum measurement appears to create an irreversible flow of time, turning potential futures into actual past. This is deeply mysterious. What counts as a measurement? Is it the interaction with a conscious observer? Is it any interaction with a large classical object? Is it something else entirely? Different interpretations of quantum mechanics give different answers. Some physicists, like Hugh Everett, suggested that wave functions never actually collapse. Instead, every measurement causes the universe to split into multiple branches, each containing one of the possible outcomes. You measure the electron's position, and the universe branches into versions where you found it in each possible location. In this many worlds interpretation, all possibilities are realized, just in different branches of reality. If that's true, then time doesn't have a single trajectory. It branches, fractals, multiplies with every quantum event. And there are countless quantum events happening everywhere, every moment. Your present moment is just one branch of an inconceivably vast tree of possibilities. Whether wave functions collapse, or the universe splits, or something else entirely happens, the quantum measurement problem shows us that time, consciousness, and reality are intertwined in ways we don't fully understand. The flow of time, the fixing of the past, the opening of the future, these might all be connected to the strange behavior of quantum systems and the act of observation itself. We've journeyed deep into the quantum realm, where time behaves in ways that seem impossible from our everyday perspective. We've learned that time becomes uncertain and probabilistic at the smallest scales, that entangled particles share connections that transcend space, that time crystals create patterns that repeat in the temporal dimension, that there may be a shortest meaningful moment called Planck time, that antiparticles can be seen as particles moving backward through time, that waves might travel both forward and backward, creating a handshake across time, and that quantum measurement itself might be what creates the irreversible flow of time we experience. The quantum world doesn't just add strange details to our understanding of time. It fundamentally challenges what time is and how it works. At the deepest levels of reality, time may not be what it seems at all. In our next segment, we'll zoom back out from the quantum realm and look at time on the largest scales. We'll explore how time works near black holes, what happens to time in different parts of the universe, and whether time might be an illusion, not something fundamental, but something that emerges from deeper, timeless laws. For now, rest in the knowledge that you are a quantum being, made of particles that dance to the strange rules of the quantum realm, existing in a present moment that emerges from the mysterious interaction of measurement, superposition, and the flow of possibilities into actualities. Breathe, wonder, and when you're ready, we'll continue our journey together. Part 3. Time at the cosmic scale. Welcome back. In our first segment, we explored how time began with the Big Bang and learned about Einstein's revelations that time is relative, bendable, woven together with space. In our second segment, we ventured into the quantum realm, where time becomes uncertain, where particles can influence each other across vast distances, and where the very act of measurement might create time's flow. Now, we're going to expand our view to the largest scales imaginable. We'll look at time across the entire cosmos, at how it behaves near the most extreme objects in the universe, and at what time means when you consider the universe as a whole. So settle back, let your imagination expand to cosmic proportions, and prepare to explore time on scales so vast that human lifetimes become less than the blink of an eye. Imagine falling toward a black hole. As you get closer and closer to this cosmic monster, something extraordinary happens to time. From your perspective, falling inward, things seem relatively normal, at least at first. But to someone watching you from a safe distance, something very different is happening. As you approach the event horizon, the point of no return surrounding the black hole, you appear to slow down. Your movements become sluggish. Your clock ticks more and more slowly. The light reaching the distant observer becomes increasingly redshifted, stretched to longer and longer wavelengths. And then, as you reach the event horizon itself, you appear to freeze completely. From the distant observer's perspective, you never actually cross the horizon. You seem to hover there forever, your image fading and reddening, but never quite disappearing. Time for you at the event horizon has stopped completely from their point of view. At the event horizon of a black hole, time dilation becomes infinite from an outside perspective. This is gravitational time dilation taken to its ultimate extreme. The gravity is so intense that time itself grinds to a halt. But here's what's truly strange. From your perspective, falling in, none of this happens. You sail right through the event horizon in a finite amount of time. You don't feel anything special at that moment. You don't freeze. Time continues to flow for you normally. It's only from the outside that time appears to stop. This creates a profound asymmetry in the universe. The inside of a black hole is causally disconnected from the outside. No information, no light, no influence of any kind can escape from inside the event horizon. It's a one-way membrane in space-time. Things can fall in, but nothing can come out. And once inside, time and space switch roles in a sense. Inside a black hole, You can no more avoid moving toward the singularity at the center than you can avoid moving forward in time in the normal universe. The singularity isn't a place in space. It's a moment in your future, unavoidable and approaching. Time inside a black hole points toward destruction. Let's zoom out from black holes and consider the universe as a whole. The universe is expanding. Galaxies are moving away from each other, not because they're traveling through space, but because space itself is growing. This expansion began with the Big Bang 13.8 billion years ago. At that moment, the universe was infinitely dense and hot, and it has been expanding and cooling ever since. But here's a question that might seem simple but has a profound answer. What is the universe expanding into? The answer is nothing. The universe isn't expanding into anything. Space itself is what's expanding. There's no outside for the universe to expand into. The expansion is an expansion of space, not an expansion through space. And time? As the universe expands, the fabric of space-time stretches, and time becomes part of this cosmic evolution. The age of the universe, the duration since the Big Bang, is measured in cosmic time, the time experienced by observers who are at rest with respect to the cosmic microwave background radiation, the afterglow of the Big Bang. Different observers moving at different speeds through the universe will measure different amounts of elapsed time since the Big Bang. But there's a special reference frame, the one in which the cosmic microwave background appears the same in all directions. In this frame, the universe is 13.8 billion years old. This is cosmic time, the clock of the universe itself. The expansion of the universe has another strange consequence for time. Light from distant galaxies is stretched as space expands during the light's journey to us. This cosmological redshift tells us how much the universe has expanded since the light was emitted. By measuring the redshift, we can determine when in cosmic time the light began its journey. The most distant galaxies we observe are seen as they were over 13 billion years ago, when the universe was young and small. We're literally looking backward in cosmic time. The farther we look into space, the farther we look into the past. Our telescopes are time machines, showing us the history of the universe written in light. There's a signal that fills the entire universe, coming from every direction in space. It's faint, just a whisper of microwave radiation, but it's everywhere. This is the cosmic microwave background, or CMB, and it's one of the most important pieces of evidence we have about the history of the universe and the nature of time. The CMB is light that was released approximately 380,000 years after the Big Bang. Before that moment, the universe was so hot and dense that atoms couldn't form. Electrons and atomic nuclei existed separately, and light couldn't travel far without being scattered by these free electrons. The universe was opaque, like being inside a thick fog. But as the universe expanded and cooled, it reached a temperature where electrons and nuclei could combine to form neutral atoms. This moment is called recombination. When it happened, light could suddenly travel freely through space. The universe became transparent. The cosmic microwave background is light from the moment the universe became transparent, and it has been traveling through space for over 13 billion years. That light has been stretched by the expansion of the universe from visible light to microwaves, but it's still here, filling space, carrying information about what the universe was like in its infancy. When we observe the CMB, we're seeing a snapshot of the entire observable universe from a specific moment in cosmic time. We're looking at a surface in space-time called the surface of last scattering. This is as far back in time as we can see with light. Before recombination, the universe was opaque, so there's no earlier light to observe. In a very real sense, the CMB represents a kind of cosmic time stamp. It shows us what the universe looked like at t = 380,000 years. The tiny fluctuations in the CMB's temperature in different directions show the seeds of structure that would eventually grow into galaxies and galaxy clusters. We're seeing the baby picture of the universe, the earliest possible photograph, looking back across billions of years of cosmic time. We've talked about the beginning of time, but what about the end? Will time go on forever, or might it come to a stop? The answer depends on what happens to the universe in the far, far future. According to our best current understanding, the universe will continue to expand forever, accelerating as it goes, driven by something called dark energy. As this expansion continues over trillions and trillions of years, stars will burn out. New stars will stop forming as gas and dust are used up. Galaxies will drift apart, accelerating away from each other until they disappear beyond each other's cosmic horizons. Black holes will slowly evaporate through a process called Hawking radiation, disappearing over timescales of 10 to the power of 100 years or more. Eventually, after an unimaginable duration, the universe will reach a state called heat death. In the heat death of the universe, all energy becomes evenly distributed, entropy reaches its maximum, and no more change is possible. Everything reaches the same temperature, the same energy level. There are no gradients, no differences, no structure. And without change, without difference, without events happening, time loses its meaning. If nothing can happen, if the universe has reached a state of maximum entropy where no further increase in disorder is possible, then in what sense can we say that time continues to pass? The arrow of time, remember, points in the direction of increasing entropy. But if entropy has reached its maximum and cannot increase further, the arrow disappears. There's no way to distinguish one moment from the next because nothing changes. Past, present, and future become meaningless categories in a universe that has reached perfect equilibrium. This is the ultimate fate of time according to our current understanding. Not a dramatic ending, but a fading away into changelessness. Time doesn't stop in a sudden moment. It gradually becomes meaningless as the universe runs down, like a clock that slows and finally stops ticking because its spring has unwound completely. But this is trillions upon trillions of years in the future, a time span so vast that the entire history of the universe, so far, is just the tiniest first moment. And there's still much we don't understand about dark energy and the ultimate fate of the cosmos, so this prediction could change as our knowledge grows. Now, let's consider a truly radical idea that has emerged from attempts to understand quantum gravity and black holes. It's called the holographic principle, and it suggests something extraordinary about the nature of reality and time. You've probably seen a hologram, a two-dimensional surface that contains all the information needed to create a three-dimensional image. The holographic principle suggests that our entire universe might work the same way. All the information about what happens in a volume of space might be encoded on the surface that bounds that volume. This idea came from studying black holes. Physicist Stephen Hawking realized that black holes have entropy, a measure of disorder and information. Jacob Bekenstein showed that this entropy is proportional to the surface area of the event horizon, not the volume inside. The bigger the black hole's surface, the more information it contains. This was surprising. Normally, we'd expect the amount of information in a region to be proportional to its volume. More space means more room for information. But for black holes, it's the surface area that matters. Physicists began to wonder, might this be true for the universe as a whole? Perhaps the three-dimensional reality we experience is actually a projection of information encoded on a two-dimensional boundary far away. Like a hologram, our 3D world might emerge from 2D information. And time? In this holographic description, time might not be fundamental at all. It might be something that emerges from the way information is organized and processed on the holographic boundary. The flow of time, the progression from past to future, might be an illusion created by the way the hologram is constructed. Some physicists think this could solve the problem of reconciling quantum mechanics and gravity. Maybe space-time itself, including time, isn't fundamental. Maybe it emerges from something deeper, something that doesn't involve space or time at all. Time would be like temperature, not a fundamental quantity, but something that emerges from the collective behavior of underlying components. This is still speculative, still at the cutting edge of theoretical research. But it represents a profound possibility that time, which seems so real and fundamental to our experience, might be a projection, an emergent property of a deeper reality that is itself timeless. We've mentioned that at the Planck scale, space-time might not be continuous, but might come in discrete units. One of the leading theories that explores this idea is called loop quantum gravity. In loop quantum gravity, space is not a smooth continuum, but a network of discrete loops, like a fabric woven from tiny threads. These loops are incredibly small, at the Planck scale, far too small to ever observe directly. But they form the basic structure from which space emerges. And time? In loop quantum gravity, time also becomes discrete at the fundamental level, flowing in minimal Planck time steps rather than continuously. Reality, in this theory, is more like a film strip with individual frames than like a smoothly flowing river. This has profound implications. If time is discrete, then the Planck time truly is the shortest meaningful interval. You cannot have an event that takes half a Planck time. Time advances in quantum jumps, indivisible ticks of a cosmic clock. Loop quantum gravity also suggests something remarkable about the Big Bang. In Einstein's general relativity, if you trace the expansion of the universe backward in time, you reach a singularity, a point of infinite density where the laws of physics break down. But in loop quantum gravity, the extreme quantum effects at the Planck scale prevent this singularity from forming. Instead, the universe might have bounced. Before our Big Bang, there might have been a previous universe, contracting under gravity until it reached Planck density. Then quantum effects would have caused it to rebound, expanding outward in what we call the Big Bang. Time wouldn't have begun absolutely. It would have just entered a new phase. In some versions of loop quantum gravity, time before the Big Bang might have been running backward. The bounce would be a moment where the direction of time reversed. This is highly speculative, but it shows how different theories of quantum gravity lead to radically different pictures of what time is and how it behaves at the most fundamental level. Here's another mind-bending cosmological idea: eternal inflation. To understand it, we need to talk about the inflationary period in the very early universe. In the first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion called inflation. In less than a trillionth of a trillionth of a trillionth of a second, the universe grew from smaller than an atom to roughly the size of a grapefruit. This inflation smoothed out the universe and explains why it looks so uniform in different directions. But here's the strange part. Once inflation starts in one region, it might never completely stop everywhere. In some places, inflation ends, and those regions become normal expanding universes like ours, filled with matter and radiation. But in other places, inflation continues, and those regions keep inflating, growing exponentially. In eternal inflation, new universes are constantly being created as inflation ends in different regions, forming an infinite multiverse. Our universe is just one bubble in an infinite sea of bubbles, each with its own Big Bang, its own expansion, its own timeline. Each bubble universe has its own cosmic time, its own clock that started when inflation ended in that particular region. But these clocks don't all start at the same moment in some universal time. There's no overarching cosmic time that encompasses all the universes. Each universe has its own independent time. Moreover, the properties of physics itself might be different in different bubble universes. The constants of nature, the strength of fundamental forces, even the number of spatial dimensions might vary. Some universes might have time that works differently than ours. Some might have multiple time dimensions. Some might have no time at all, existing in a timeless, static state. From outside the system, if such a perspective even makes sense, the multiverse is eternal. Inflation has been happening forever in the past and will continue forever in the future, constantly creating new universes. But inside each individual universe, time has a beginning, a Big Bang, where that universe's clock started ticking. This idea is controversial and perhaps untestable, since we can't observe other bubble universes outside our own. But it represents one possible answer to the question of what came before the Big Bang, an eternally inflating multiverse, creating universes without beginning or end. We've traveled across cosmic scales and cosmic time. We've seen how time stops at black hole event horizons, how it's woven into the expansion of the universe, how the cosmic microwave background gives us a snapshot from deep in cosmic time, how time might eventually become meaningless in the heat death of the universe, how the holographic principle suggests time might not be fundamental, how loop quantum gravity proposes that time is discrete. and how eternal inflation implies an infinite multiverse with countless independent timelines. Time, viewed from these cosmic perspectives, is not a simple, universal flow. It's entangled with the structure of the universe itself, with the expansion of space, with the curvature caused by matter and energy, with the quantum nature of reality at the smallest scales. In our next segment, we'll explore something even more personal: how living beings experience time. We'll discover why time seems to speed up as we age, how our brains construct the feeling of now, and whether consciousness itself might be intimately connected to the flow of time. For now, contemplate your place in this vast cosmic story. You exist in a bubble of space-time, born in a Big Bang 13.8 billion years ago, riding the expansion of space, experiencing your own local flow of time, part of a universe that had a beginning and will have an ending, playing out your brief existence in the grand cosmic timeline. Rest in that vastness. Feel the ancient starlight that has traveled for billions of years to reach your eyes. And when you're ready, we'll continue our journey together. Part 4. The Biology and Psychology of Time. Welcome back to our exploration of time. We've journeyed from the birth of time in the Big Bang, through the quantum realm where time becomes uncertain and strange, to the cosmic scales where time bends around black holes and stretches with the universe itself. Now, we're going to bring our focus closer to home. We're going to explore how you, as a living being, experience time. Because the time you experience isn't just the abstract time of physics. It's filtered through your biology, shaped by your psychology, colored by your emotions and memories. The time you live is personal, subjective, uniquely yours. So take a moment to settle into your own experience of this present moment. Feel time passing as you listen. Notice how your perception of time colors every aspect of your existence. And let's explore together the strange science of how living beings experience time. Why time speeds up as you age. Think back to when you were a child. Remember how long summer vacations seemed? How an hour could feel like an eternity? How the wait for a birthday or holiday stretched on endlessly. Now, as an adult, you might feel like years fly by in the blink of an eye. Weeks blend together. Decades seem to pass faster than those childhood summers. Time, it seems, accelerates as we age. This isn't your imagination. It's a well-documented psychological phenomenon. As we age, our perception of time's passage accelerates, making years seem shorter and shorter. A year to a 5-year-old represents 1/5 of their entire life. A year to a 50-year-old is just 1/50th of their life experience. This proportional theory, first proposed by psychologist Paul Janet in 1897, suggests that we judge duration relative to our total lifespan. The longer you've lived, the smaller each new period of time seems in comparison. But there's more to it than simple proportion. As we age, we encounter fewer novel experiences. Think about childhood. Everything was new. The first day of school, the first time riding a bike, learning to read. Each new experience creates rich, detailed memories that make time feel expansive. As adults, we fall into routines. Days become similar. We drive the same route to work, eat similar meals, follow predictable patterns. Our brains, being efficient, don't store as much detail about routine experiences. Without those rich, varied memories, time in retrospect seems to have passed quickly. Looking back, weeks blur together because nothing distinctive marks them. Novelty slows down perceived time. When you travel to a new place, learn a new skill, or have novel experiences, time seems to expand again. Those days feel longer, both while you're living them and when you remember them. The more attention your brain pays, the more memories it creates, the longer that period of time feels. So here's a beautiful insight. If you want time to feel slower, to feel like you're truly living rather than watching life rush past, seek novelty. Break routines. Pay attention. Create distinctive memories. The quality of your attention shapes your experience of time itself. The 3-second window of now. You experience the present moment as a kind of extended now. It's not an infinitesimally thin instant, but a window with some duration. You can hear a melody, not just individual notes. You can follow a sentence, not just isolated words. You experience events as happening now, even though they unfold over a brief period. Scientists have found that this psychological present, this window of now, lasts approximately 3 seconds for most people. The human brain integrates sensory information over roughly a 3-second window to create the experience of the present moment. This was discovered through studying many different aspects of human behavior. When people are asked to tap a regular rhythm without external cues, they naturally settle into intervals around 3 seconds. When people are asked to estimate when now is, they tend to include events from about the last 3 seconds. Across many cultures and contexts, this 3-second window appears consistently. Even in language and music, we see this pattern. A typical line of poetry or a musical phrase tends to last around 3 seconds. It's as if human expression naturally fits within the window of the psychological present. But this window isn't fixed for everyone at all times. When you're engaged, focused, in a flow state, your window of now might compress, allowing you to process information more rapidly. Athletes in the zone often report that time seems to slow down, giving them more time to react. Their 3-second window is processing more information, making it feel stretched out. In altered states, through meditation or certain substances or neurological conditions, the window can change dramatically. Some people report the present moment expanding to feel timeless, boundless. Others experience it fragmenting, making it hard to connect events into coherent sequences. Your brain is constantly constructing your experience of now from streams of sensory information that arrive at slightly different times. Light from a distant object, sound from nearby, the feeling of your body, these all take different amounts of time to process. Yet your brain stitches them together into a unified experience of this moment, happening now, all at once. The 3-second window is how long your brain takes to weave these threads into the tapestry of your present experience. Chronobiology. The clocks within your body. You have clocks inside you. Not metaphorical clocks, but actual biological timekeeping mechanisms that run constantly, regulating your body's functions across different timescales. The most famous is your circadian rhythm, your approximately 24-hour internal clock that regulates sleep and wakefulness. This clock is controlled by a tiny region of the brain called the suprachiasmatic nucleus, which contains about 20,000 neurons that fire in coordinated patterns across the day. Living organisms have internal biological clocks that regulate functions on various timescales, from milliseconds to years. These clocks don't just passively respond to external time cues. They actively keep time, continuing to cycle even in the absence of external signals. If you were placed in a cave with no sunlight, no clocks, no way to tell time, your circadian rhythm would continue. You'd naturally settle into a sleep-wake cycle, though it might drift slightly from exactly 24 hours. Your body temperature would rise and fall in a daily pattern. Certain hormones would surge and ebb on schedule. Your internal clock would keep ticking. But circadian rhythms are just the beginning. You have ultradian rhythms that cycle multiple times per day, controlling things like your alertness, hunger, and hormonal fluctuations. You have infradian rhythms that take longer than a day, like monthly hormonal cycles or seasonal patterns of mood and behavior. Even individual cells have their own clocks. Almost every cell in your body contains clock genes that turn on and off in rhythmic patterns, regulating when that cell performs various functions. Your liver cells know what time it is. Your heart cells keep their own schedule. You are a symphony of overlapping temporal rhythms. What's remarkable is that these biological clocks are inherited from billions of years of evolution. Even single-celled organisms like cyanobacteria have circadian rhythms. Life has been keeping time since the very beginning, synchronizing internal processes with the day-night cycle of a rotating Earth. Your experience of time is not just psychological. It's deeply biological, written into your genes, expressed in the rhythms of your cells, manifested in the rise and fall of your energy and alertness throughout the day. You are a temporal being, carrying the clock of evolution within you. The neuroscience of time perception. How does your brain actually perceive time? How do you know that one event happened before another? How do you estimate durations? The answer is, there's no single clock in your brain. Unlike a computer with a central processor that times everything, your brain uses distributed timing mechanisms. Different regions process time in different ways for different purposes. For very short intervals, milliseconds to seconds, your brain uses the patterns of neural firing. The brain perceives short durations through the synchronized firing patterns of neurons, not through a central clock. Groups of neurons fire in sequences and rhythms, and your brain reads these patterns as representing time. This is why drugs that affect neurotransmitters can distort time perception. If the neurons fire faster, time might seem to move slowly because more neural events are happening per objective second. If they fire more slowly, time might seem to speed up. For longer intervals, seconds to minutes, your brain seems to use working memory. The more information you can hold and process in working memory, the longer that period seems to last. This is why time drags when you're bored. You're not processing much, so there's not much to mark the passage of time. It's also why time flies when you're engaged. You're processing so much that you don't notice time passing. For even longer periods, hours to days to years, your brain relies on memory. You estimate how long ago something happened based on how many memories you have between then and now. This is why time seems to speed up with age. Fewer distinctive memories make periods seem shorter in retrospect. Interestingly, your brain's perception of time can be manipulated surprisingly easily. If you're shown a series of images rapidly, with one image repeated, that repeated image will seem to last longer than the others, even though they're all displayed for the same duration. This is called the oddball effect. Your brain pays more attention to the novel stimulus, creating more detailed processing, which makes it seem to last longer. Your brain also has specialized circuits for anticipating time. When you press a button, your brain predicts when the result will occur. If there's a delay, you notice immediately. This predictive timing is crucial for movement, for language, for music, for anything that unfolds in time and requires coordination. Time perception isn't passive reception. It's active construction. Your brain is constantly predicting, estimating, adjusting its model of when things are happening and how long they last. And this construction can be wrong, can be fooled, can vary based on your state of mind and what you're paying attention to. Flow states, when time disappears. Have you ever been so absorbed in an activity that hours passed without you noticing? Maybe you were playing music, writing, coding, rock climbing, painting, playing a game. You were completely focused, effortlessly performing, not thinking about yourself or about time. And then suddenly you looked up and realized it was much later than you thought. This is called a flow state, and it's one of the most interesting phenomena in the psychology of time. In flow states, people lose track of time as their attention becomes completely absorbed in the present activity. Psychologist Mihai Csikszentmihalyi, who pioneered the study of flow, found that these states occur when several conditions are met. The task must be challenging but not too difficult. It should stretch your skills without overwhelming them. You need clear goals and immediate feedback. You need to feel in control. And the activity should be intrinsically rewarding, worth doing for its own sake. When these conditions align, something remarkable happens to your experience of time. The normal self-monitoring that occupies part of your attention falls away. You're not thinking about how you're doing or what others think or what time it is. All your cognitive resources are devoted to the task at hand. In this state, your 3-second window of now might actually expand or change. Athletes in flow often report that time seems to slow down. A baseball player sees the ball approaching in slow motion, with plenty of time to decide whether to swing. A race car driver perceives more time to react to obstacles. What's happening is that their rate of information processing has increased, packing more perceptions and decisions into each objective second. Flow states show us that our normal experience of time is just one possibility. By changing how we engage with activities, by finding that sweet spot of challenge and skill, we can alter our relationship with time. We can make it disappear, or we can make it slow down and expand, giving us the subjective experience of more time to live and act. This has profound implications. It suggests that the richness of your life, the amount of experience you pack into your years, isn't determined by the number of minutes and hours you have. It's determined by how deeply you engage with those moments. A life lived in frequent flow might contain more subjective experience than a life of passive consumption, even if both lives have the same objective duration. Time perception across species. We've been talking about human time perception, but what about other animals? Do they experience time the way we do? The answer is fascinating. Different species appear to experience time at different rates. Different animals perceive time at different speeds based on their metabolic rate and the rate at which their nervous systems process information. Scientists measure this using something called critical flicker fusion frequency. This is the rate at which a flashing light needs to flicker before an animal perceives it as continuous rather than flashing. Animals with higher flicker fusion frequencies can detect faster changes. They process visual information more quickly. Small animals with fast metabolisms, like flies and hummingbirds, have high flicker fusion frequencies. To a fly, your hand swatting at it appears to move in slow motion, giving it plenty of time to dodge. This is why flies are so hard to swat. From their perspective, you're moving incredibly slowly. Dogs process visual information about 25% faster than humans. That's why they have trouble watching television at standard frame rates. They see the individual frames flickering rather than smooth motion. Modern high frame rate displays work better for them. Larger animals with slower metabolisms, like turtles and elephants, have lower flicker fusion frequencies. They process information more slowly. To a turtle, the world might seem to move slightly faster than it does to you. This makes sense from an evolutionary perspective. If you're small, you need to react quickly to survive. Fast predators, fast escape responses, they all require processing the world rapidly. So small animals live in what is effectively fast forward compared to larger animals. The relationship extends beyond just vision. Small animals with fast metabolisms have shorter lifespans but pack in more heartbeats, more breaths, more neural events per unit time. In terms of subjective experience, in terms of the number of moments they live through, they might experience as much life in a few years as a large animal does in decades. Time is not objective for conscious beings. It's scaled to the speed at which your nervous system operates. A second is not the same experiential duration for a fly, a human, and an elephant. We each inhabit our own temporal worlds, moving through the same objective time at different subjective speeds. The memory-time connection. Why time flies when you're having fun? There's a curious paradox in how we experience time. When you're having fun, engaged, enjoying yourself, time seems to fly by. The hours vanish. You're surprised when you check the clock. But then, later, when you look back on that experience, it seems to have lasted a long time. You have rich, detailed memories. Conversely, when you're bored, time drags. Each minute feels endless. You check the clock repeatedly, but afterward, that boring period seems short in memory. It's as if it barely happened. Time perception has a paradoxical relationship with memory. Time flies during enjoyable experiences, but seems long in retrospect, while boring experiences drag on, but seem short in memory. This paradox reveals something important about how we experience time in two different modes, perspective and retrospective. Perspective time is time as you're living it moment by moment. In this mode, Attention is key. When you're paying close attention to time itself, watching the clock, waiting for something to happen, time seems to move slowly. There's not much happening, so each moment feels stretched out. When you're absorbed in an activity, not paying attention to time, it rushes past. You're focused on what you're doing, not on the passage of time, so you don't notice it flowing by. Retrospective time is time as you remember it, looking back. In this mode, memory is key. The more memories you have of a period, the longer that period seems to have been. Rich, detailed, varied memories make time feel expansive in retrospect. Enjoyable, novel experiences create lots of memories, so they seem long when you look back on them, even though they flew by while you were living them. Boring, routine experiences create few memories, so they seem short when you look back, even though they dragged on while you were living them. This is why vacations seem to last a long time even though they fly by. It's why years of routine work blur together and seem short. The richness of your memories shapes your sense of how much time you've lived. This suggests a strategy for living a life that feels long and full. Seek novelty, create memorable experiences, pay attention, engage deeply. A life of routine might be comfortable, but it will feel short in retrospect. A life of varied experiences, even if sometimes challenging, will feel rich and expansive when you look back on it. Your experience of time is intimately connected to your experience of life itself. To live richly is to experience time richly. We've explored the deeply personal nature of time in this segment. We've learned why time seems to speed up as we age, discovered the 3-second window that our brains use to construct the present moment, explored the biological clocks that run throughout our bodies, examined how our brains perceive time through distributed neural mechanisms, investigated flow states where time disappears or expands, seen how different species experience time at different speeds, and uncovered the memory-time paradox that shapes how we experience duration. Time is not just an external reality measured by clocks. It's an internal experience, constructed by your brain, shaped by your attention and memory, influenced by your emotions and engagement. The time you live is uniquely yours, colored by your biology and psychology. In our next segment, we'll explore even stranger territory, the possibility of time travel, the paradoxes it creates, and whether the laws of physics might allow us to journey into the past or future. We'll also look at whether time might not be fundamental at all, but something that emerges from deeper timeless laws. For now, simply notice your own experience of time. Feel this present moment, this 3-second window of now. Notice how your attention shapes your sense of time's passage.
You are not just in time.
You are creating your experience of time with every moment of awareness.
Breathe.
Be present. And when you're ready, we'll continue our journey together. Part 5. Time Travel and the Deep Nature of Time. Welcome back. We've journeyed far together, from the birth of time itself, through the quantum realm, across cosmic scales, into the biological and psychological dimensions of how we experience time. Now we arrive at questions that have captivated human imagination for as long as we've been aware of time's passage. Can we travel through time? Can we visit the past? journey to the future? What paradoxes would such travel create? And perhaps most profound of all, is time even real? Or might it be an illusion? Something that emerges from deeper laws that are themselves timeless? These questions take us to the very edge of what science can tell us about the nature of reality. So settle in. Open your mind to possibilities that might seem impossible, and let's explore together the deepest mysteries of time. Time travel to the future, already possible. Here's something that might surprise you. Time travel to the future is not only possible, it's been done. It happens constantly. And the method is straightforward. Move fast or go somewhere with strong gravity. We discussed time dilation earlier, how moving at high speeds or being in strong gravitational fields slows down your experience of time relative to the rest of the universe. This isn't just theory. It's practical time travel to the future. Time travel to the future is already possible through time dilation and has been demonstrated with atomic clocks and particles. Russian cosmonaut Sergei Krikalev spent 803 days in orbit aboard the International Space Station, moving at about 17,000 miles per hour. Because of his speed and the slightly weaker gravity in orbit, he experienced time slightly more slowly than people on Earth. When he returned, he had aged about 0.02 seconds less than he would have if he'd stayed on Earth. He traveled 0.02 seconds into the future. It's a tiny amount, but it's real-time travel. If you could build a spacecraft capable of traveling at 99.99% the speed of light, you could travel centuries or millennia into Earth's future while experiencing only months or years yourself. You could visit the year 3000, then 4000, then 5000, jumping forward through Earth's timeline while aging normally. The physics is clear. The engineering is the challenge. Accelerating anything with mass to such high speeds requires enormous energy. But there's no law of physics preventing it. Given sufficient energy and technology, forward time travel is absolutely possible. There's also another method. Get close to a black hole. Near the event horizon, where gravity is intensely strong, time slows dramatically relative to distant observers. You could orbit close to a black hole for what feels like an hour, then return to find that years or decades have passed for the rest of the universe. The movie Interstellar portrayed this beautifully, with astronauts visiting a planet near a black hole where 1 hour equals 7 years on Earth. This isn't science fiction, it's relativity. Forward time travel is real, proven, and waiting only for the technology to make it practical on human scales. The future is accessible to anyone willing and able to move fast enough or fall deep enough into a gravitational well. The paradoxes of traveling to the past. But what about traveling backward in time? This is where things get truly strange and where physics becomes uncertain. The most famous problem with backward time travel is the grandfather paradox. If you could travel to the past, you could potentially prevent your own existence, creating a logical impossibility. Imagine traveling back in time and preventing your grandparents from meeting. Then you would never be born. But if you were never born, you couldn't have traveled back in time to prevent their meeting. But if you didn't prevent their meeting, you would be born and could travel back to prevent it. And so on, in an infinite loop of contradiction. This paradox has troubled physicists and philosophers for decades. There are several proposed solutions, each stranger than the last. One solution: self-consistency. Perhaps the universe simply doesn't allow events that would create paradoxes. If you tried to prevent your grandparents from meeting, something would always go wrong. You'd miss your flight, or they'd meet anyway through some other circumstance, or you'd accidentally cause their meeting while trying to prevent it. The timeline would protect itself, forcing events to unfold in a way that's logically consistent. This is called the Novikov self-consistency principle. It suggests that if time travel to the past is possible, only self-consistent timelines can exist. You have free will, but your actions are constrained by the requirement that you cannot change the past that led to you traveling back in time. Another solution: parallel universes. When you travel to the past, you don't enter your own past. You enter a different timeline, a parallel universe. In this new universe, you can change events without creating a paradox, because this timeline's future is independent of your original timeline. You prevent your grandparents from meeting, but that just means in this timeline, a version of you is never born. Your existence in your original timeline is unaffected. This many worlds interpretation of time travel sidesteps paradoxes, but creates its own strangeness. It means the past you visit isn't really your past, and it raises questions about whether you could ever return to your original timeline. A third possibility: time travel to the past is simply impossible. The laws of physics might forbid it. Closed time-like curves, when physics permits time loops. Here's where things get really interesting. While backward time travel seems paradoxical, general relativity, our best theory of gravity and space-time, actually permits solutions that include closed time-like curves, or CTCs. A closed time-like curve is a path through space-time that loops back on itself in time. If you followed a CTC, you would move forward through time from your perspective, but you would eventually arrive back at an earlier moment in your own timeline. Einstein's equations allow for closed time-like curves, paths through space-time that loop back to earlier times. Several solutions to Einstein's equations contain CTCs. The Gödel universe, proposed by mathematician Kurt Gödel in 1949, is a rotating universe where CTCs exist everywhere. You could travel in a spaceship and arrive back before you left. Rotating black holes, called Kerr black holes, might contain CTCs in their inner regions. Traversable wormholes, if they could exist, might be manipulated to create time machines. Even infinitely long, rotating cylinders of dense matter, called Tipler cylinders, could theoretically create CTCs in their vicinity. But here's the crucial question. Just because the mathematics allows these solutions, does that mean they can exist in our universe? Most physicists are skeptical. Every known way to create CTCs requires exotic conditions, negative energy density, infinitely long structures, naked singularities without event horizons. These might be mathematically possible, but physically impossible. Stephen Hawking proposed the chronology protection conjecture. The laws of physics conspire to prevent time travel to the past. Whenever you try to create CTCs, quantum effects create runaway feedback that destroys the time machine before it can function. The universe protects its own chronology. But we don't have a complete theory of quantum gravity, so we can't be certain. It's possible that the full theory, when we discover it, will either permit backward time travel under certain conditions, or will rule it out completely. For now, it remains one of the great open questions in physics. Let's step back and ask a deeper question about the nature of time. When we think about time, we usually imagine the past as fixed and gone, the present is real and happening now, and the future as open and undetermined. But relativity suggests something very different. Remember that there's no universal present moment. Events that one observer considers present, another observer in motion might consider past or future. If there's no objective now, what does that mean for the nature of time? The block universe view suggests that past, present, and future all exist equally in a four-dimensional space-time block. From this perspective, time doesn't flow. All moments exist simultaneously, like different frames of a film strip all existing at once. Imagine space-time as a loaf of bread. Each slice represents the entire universe at one moment in time. All the slices exist together in the complete loaf. Your life is a world line threading through the loaf, connecting your birth to your death. From outside the loaf, from a perspective that could see all of space-time at once, your entire life, past, present, and future, exists all at once. This view is sometimes called eternalism. Nothing comes into being or ceases to exist. Everything that ever happens is eternally part of the space-time block. The present moment feels special to you only because you're experiencing one slice at a time. But all slices are equally real. This has profound implications. If the future exists in the block universe as solidly as the past, is it already determined? Is free will an illusion? Are you simply moving along a predetermined world line through space-time, unable to change your trajectory? Not necessarily. Even in the block universe, there could be branching timelines, quantum indeterminacy, or other sources of openness. The future could exist without being uniquely determined. But the block universe view does challenge our intuitive sense that the present is somehow more real than the past or future. Many physicists find the block universe compelling because it fits naturally with relativity. But it's deeply counterintuitive. It suggests that the flow of time, the sense of moving from past to future, is a feature of consciousness, not of reality itself. Now, let's consider an even more radical possibility. What if time isn't fundamental at all? What if time emerges from something deeper, something timeless? This idea has gained traction in recent years as physicists have tried to reconcile quantum mechanics with general relativity. When you try to describe the universe at the very smallest scales, at the moment of the Big Bang, or inside black holes, time becomes problematic. It's hard to define. It becomes mixed up with other variables. It seems to disappear. Some theories suggest that time is not fundamental but emerges from timeless quantum interactions at the deepest level of reality. Just as temperature emerges from the random motion of molecules, time might emerge from deeper processes that are themselves timeless. In some approaches to quantum gravity, the fundamental equations have no time variable. They describe relationships between different aspects of the universe, but these relationships don't unfold in time. Time is absent from the fundamental description. How, then, do we experience time? The idea is that time emerges when you look at the universe at larger scales, when you consider systems with many particles, when you take into account thermodynamics and entropy. Time, in this view, is not a fundamental feature of reality, but a thermodynamic phenomenon connected to the increase of entropy. Think of it this way. The fundamental laws of physics are time-symmetric. They work the same whether you run them forward or backward. But thermodynamics introduces an arrow, a direction, because entropy increases. This increase of entropy might be what creates our experience of time flowing from past to future. At the deepest level, in the timeless quantum realm, there is no before or after. There are only relationships, correlations, quantum entanglements. Time emerges when you consider how these relationships manifest at larger scales, creating the thermodynamic arrow and the apparent flow we experience. This is still speculative, still being debated and researched. But it represents a profound shift in thinking about time. Rather than being one of the fundamental dimensions of reality, time might be an illusion, a useful fiction that emerges at the scales we inhabit, but dissolves when you look at the deepest structure of the universe. Here's another perspective on the non-fundamental nature of time, this time from mathematics and physics. The laws of physics are typically written as equations that describe how things change in time. But there's another way to formulate them, as timeless mathematical structures. Consider a thrown ball. In the usual formulation, you describe its position at each moment in time, showing how it moves. But you could also describe the entire trajectory as a timeless mathematical object, a parabola through space-time. The ball's entire path exists as a geometric shape in four-dimensional space-time. Both descriptions give the same predictions, but in the timeless formulation, nothing moves or changes. The trajectory simply is existing as a geometric object. The laws of physics can be formulated as timeless mathematical relationships rather than as descriptions of change over time. This is the basis of Julian Barber's controversial theory. Barber argues that time is an illusion. What really exists is a space of all possible configurations of the universe, all possible arrangements of particles, fields, and structures. Each configuration is a point in this vast configuration space. The universe's history is a path through configuration space, connecting one configuration to the next. But this path doesn't move through time. It's a static, timeless mathematical object. Our experience of time flowing is an illusion created by the correlations between different configurations along the path. Imagine a movie. The film strip contains all frames simultaneously. Nothing moves. But when you play it, you experience motion, change, time. Barber suggests that the universe is like a film strip, all moments existing timelessly, with our experience of time emerging from how these moments are correlated. In this view, the past doesn't exist back then and the future doesn't exist not yet. All moments exist equally in the timeless configuration space. What we call time is the particular sequence we find ourselves moving through, created by the correlations and patterns in how configurations connect to each other. This is a minority view in physics. but it's taken seriously because it offers potential solutions to problems in quantum gravity. If time isn't fundamental, some of the difficulties in unifying quantum mechanics and relativity might disappear. The psychological arrow. Does consciousness create time? We've talked about the thermodynamic arrow of time, the direction from lower to higher entropy. But there's another arrow, equally important to our experience, the psychological arrow. This is the direction from past to future defined by our conscious experience, our memories, our sense of moving forward through time. Remarkably, the psychological arrow always points the same direction as the thermodynamic arrow. We remember the past, not the future. We can influence the future, not the past. Our conscious experience flows in the direction of increasing entropy.
But why?
The psychological arrow of time, our experience of moving from past to future, might be fundamentally connected to consciousness and how our brains process information. Some philosophers and scientists have suggested that consciousness itself might be essential to time. Perhaps time doesn't truly flow except in the presence of conscious observers. Perhaps the universe exists in a timeless state, and time is the way consciousness navigates through that timeless structure. This idea connects to the measurement problem in quantum mechanics. Remember, quantum systems exist in superposition until measured, at which point they collapse into definite states. If consciousness is involved in measurement, then consciousness might be what transforms timeless quantum possibilities into the actual, time-ordered sequence of events we experience. This is highly speculative and controversial. Most physicists think consciousness is a product of brain processes, which themselves obey physical laws that include time. A consciousness experiences time. It doesn't create it. But there's a mystery here. Why does the subjective experience of time, the felt sense of now, of moving from past to future, exist at all? Why aren't we just computational systems processing information without any subjective sense of time passing? The relationship between consciousness and time remains one of the deepest puzzles in both physics and philosophy. We don't know if consciousness is fundamental to time, or if time is fundamental to consciousness, or if both emerge from something deeper still. What we do know is that your experience of time, the way you feel moments passing, the way you distinguish past from future, the way you exist in what feels like a moving present, is intimately connected to your consciousness, to your awareness itself. We've explored profound questions in this segment. We've learned that forward time travel is already possible through time dilation, confronted the paradoxes that make backward time travel problematic, discovered that Einstein's equations allow for closed time-like curves that loop through time, considered the block universe view where all moments exist equally, explored the possibility that time is not fundamental but emergent, seen how the laws of physics can be written as timeless mathematical relationships, and contemplated whether consciousness itself might be essential to the existence of time. These questions take us to the very edge of human understanding. We don't have definitive answers. We have theories, possibilities, compelling arguments, but no certainty. Time remains mysterious even after centuries of scientific investigation. In our final segment, we'll draw together everything we've learned and explore the ultimate questions. What is time really? Why does it exist? And what does understanding time teach us about how to live our lives?
For now, rest in the mystery.
You are a conscious being experiencing time, moving from moment to moment, existing in this present instant that somehow emerges from the timeless depths of reality.
Feel the strangeness of that.
Wonder at it, and when you're ready, we'll complete our journey together.